Okay, so here's the next question. A population of Drosophila melanogaster, the humble fruit fly, has 100 individuals. 40 of these have wild-type eyes, while 60 have brown eyes. Brown eyes are homozygous recessive, while wild-type eyes can be homozygous dominant or heterozygous. What is the allele frequency for the dominant allele in this population? And then, of course, assume the population is in Hardy-Weinberg equilibrium. So take a couple of minutes, go through it, and see if you can get the answer. And then afterwards, we will walk through the question and figure out how we can get to the result. Okay, so I hope everyone had a chance to actually stop and, write it out and actually figure out the problem. And this is the answer right over here, 0.225 or like 0.2254, around that. That is the answer to this question. Did you get it right? If you did, good job. If not, that's okay. And we're going to go through the question step by step right now. Okay, so same question up here. What we're really looking for in this particular question is what I consider to be sort of a working backwards problem where the population already is in Hardy-Weinberg. So earlier in the other video, we did a question where you're trying to figure out and see whether the population is in Hardy-Weinberg. In this particular problem, the population already is in Hardy-Weinberg equilibrium. And what you're trying to do is figure out the, in this case, allele frequencies given some kind of information. So let's take a look at this question. The key thing here is that you're looking for the allele frequency of the dominant allele. So the dominant allele in our case, let's just use arbitrarily big A and little a just to keep things going. That's big A. So really, this question is asking what's the frequency of big A in this population. And then, of course, assume the population is in Hardy-Weinberg equilibrium, so you can use your P plus Q and P squared, 2PQ, and Q squared equations. So as I mentioned, this is a backwards problem where you already know the population is in Hardy-Weinberg, so you can use your equations to get the result. So just arbitrarily, big A, you will have the phenotype of wild-type eyes. Big A, little a is the heterozygote, but in our case, you would also get wild-type eyes. And then, of course, little a, that's our homozygous recessive individuals, and those have the brown eyes. So big A, remember, is equal to Q. You can use, big A is equal to P, and little a is equal to Q, and you can use these values however you'd like. Again, the nomenclature can be a little bit arbitrary, but just for the sake of it, the dominant allele, let's just associate it with P, and the recessive allele, in our case, let's just associate it with Q to keep things straightforward. Although, again, this is somewhat a little bit arbitrary depending on how you approach the problem. So what is the allele frequency for the dominant allele in this population? This means you're looking for the frequency of A, aka the value of P. Remember, A equals P in our situation. So how do you do this problem? Well, first of all, you have 60 individuals with brown eyes, which means that there are 60 individuals that are little a, out of a total of 100 individuals. So that effectively means that you can do 60 divided by 100 to get 0.6. And this 0.6 is going to ultimately be our frequency of the genotype little a. Remember, this is the genotype, or the individuals. So 60 divided by 100, 0.6, that's the frequency of little a, which also happens to be the frequency of the value Q squared. We know the population is in Hardy-Weinberg equilibrium, which means we can use this Q squared value to keep going and solve for our P values. And so what do? Well, you know Q squared. You can easily find Q simply by square rooting the value of Q squared, or square root of 0.6, which in our case is 0.7745, yada, yada, yada. So our Q value is this value given over here. Now, remember, it's very important to keep in mind that the population is already in Hardy-Weinberg equilibrium, so you can use this formula over here where P is simply 1 minus Q. So P equals 1 minus 0.77459, etc., and that gets you this value, 0.2254. And so remember, P now is equal to 0.2254, and P, as we discussed before, is the same as our frequency of allele A. we are looking for the allele frequency of the dominant allele, which just in our case happens to be arbitrarily chosen as the letter A. You can use whatever, you can use B or C or whatever, but I just decided to use A. So P is the frequency of A, P equals A, so A is the allele frequency of the dominant allele for our situation, and therefore, as a result, our answer is 0.2254 or 0.225, around that, give or take. So that is how you approach this particular problem. Again, if you got it right, congratulations, good job. If you didn't get it right, it's okay. Go through it and try to solve it yourself. So again, this particular problem is very interesting because it's kind of what I consider a work backwards problem, where you already know that the population is in Hardy-Weinberg equilibrium, and you're simply working backwards to try to figure out what the other genotypes are or what the other allele frequencies are. And if you can do this kind of problem and the forward type of problem, you can pretty much solve most, if not all, of our Hardy-Weinberg questions that you usually will get in an introductory biology classroom. So try to go through it again, and best of luck, and we'll go through one more problem in another video afterwards. So best of luck, and I'll see you in the next video.